Hello, welcome to our first EY Academy meeting dedicated to quantum technology, in particular to quantum computers today. For today's meeting, we invited Ania Kamińska. Ania has a PhD in theoretical physics. Currently, she is working for Creotech Instruments, which is one of the most promising Polish technological startups working in the field of space and quantum industry. Ania?
Hello, very nice to be here with you all.
Philippe De Brouwer is also with us. Philippe has 3 decades of experience in banking. He has a PhD in financial mathematics applied to investment advice. He is now a honorary consul of Belgium in Krakow and the senior vice president of HSBC. He is a board member of both the International School of Krakow and AGH, University of Science and Technology. He recently authored a book about data science called the Big R book, From Data Science to Machine Learning and the Big Data. He teaches MBA grads and students at 4 different universities, and he is our optimist today.
Well, thank you for inviting me. It's really a pleasure to be here today, and it's an exciting opportunity. Thank you so much.
Thank you. Last but not least, Michał Oszmaniec. He is also a PhD in theoretical physics. He holds a professor position at the Center for Theoretical Physics of Polish Academy of Science, where he is a leader of quantum computing group. Michał?
Thank you, Marcin, for the introduction. It's great to be here. Yeah, I'm looking forward for the meeting.
And myself, my name is Marcin Domagała. I'm also a PhD in physics, working in quantum gravity. I'm Polish licensed actuary, and currently I'm senior manager at Global Financial Services at EY. Today, I decided to avoid phrases like revolution and like that. Undoubtedly, the use of these phrases in the context of quantum computing is fully justified, but I would like to give a completely new perspective to the topic. The quantum age is a very likely future which we cannot ignore today. The million-dollar question is, when should companies start to invest in quantum technology? While that remains unclear, it could arrive sooner than most of the people expect, and companies should start thinking seriously about what a venture into quantum may mean for them. The business that will not become quantum ready will undoubtedly lag behind in the near future. Philippe, do you think that the time to start thinking about quantum readiness have arrived?
Frankly, yes. I'm quite sure that the time has arrived. You see, we have now quantum computers. The concept works, and the concept has scaled from a few qubits to a reasonable amount of qubits, and we can do useful things with it. It reminds me of so many things. For example, when Kodak invented the digital camera, they decided the market wasn't ready for it, and now the company doesn't exist anymore. Or another thing, in the New York Times, a few hundred years ago, appeared an article saying that it would not be possible to fly with airplanes or something like that for the next 1 million to 10 million years. And they had senior scientists answering that question. 9 days later, the Wright brothers took flight.
So thank you, Philippe, for that. But Ania, professionally, you are involved in manufacturing quantum computers. Can you tell us, are these things real?
Definitely. I mean, already for some time we have commercially available quantum computers. Well, okay, quantum annealers, like the ones manufactured by D-Wave, are there for some time now, and they support 2,000 qubits, and that's quite a lot already. The Holy Grail, so the universal quantum computer, it's already there. So we have both commercially available computers in the US and also now in Europe. And of course, they are early machines. They support a small number of qubits, but you can already start working with them and developing algorithms and applications. So definitely, the time is now.
Great, thank you for that. And Michał, in the near future, we will definitely need new competences to exploit the potential of quantum computers. So among your students, your PhD students, your collaborators, probably the future leaders, the future managers who will introduce the quantum computing into the market. Do you think that those people, they are already there?
Yeah, so my team is reasonably small, like 10 person maybe. Like I have very gifted students, and I'm certain that some of them will actually introduce big change to the industry in the future. Just maybe looking more globally, we see currently the trend in academia, industry, to build up the competence that is needed for pushing quantum computing further. And it's actually, you don't only need competences in physics, mathematics, computer science, engineering, all those things, they have to be blended together. Like because of that, around the world, there are like special programs constructed and put forward. For example, by MIT, like they have a special curriculum just for that. Yeah, so like definitely we need more experts and more competence in the field.
Thank you for that. So let's start talking about quantum computers. These are the mythical machines that everyone desires today, so much that the best universities, the biggest companies, the governments, and even the European Union itself are working on them. Anya, can you tell us something about this? How the world is trying to build the real quantum computer, and what machines are there available currently?
Well, from my point of view, these machines are totally not mythical. They're like real-world hardware that we're working with on a daily basis. So, two big cabinet racks, for example, hosting a quantum computer, that's the kind of state that there is now in the field. Well, the approach is, for now, there's like no single approach on how to build a quantum computer, because the technology is so young that we are still pursuing various ways of building a quantum computer, and we don't know which one will win in the end. So we are using quantum states of matter to perform computations. So you can already see that this is going to be a totally different way of computing, a totally different approach to solving problems. Well, what do you use then? So you can use, for example, elementary particles and the energy levels of those particles as the quantum states, which will correspond to the 0 and 1, let's say. You can use really small electric circuits, and that's the superconducting qubits approach. You can use light and quantum states of light to perform computations. So these are super different approaches in terms of the physics, in terms of hardware and engineering. It's actually extremely exciting on the hardware side, and that's where my company is active. What we're working on mainly are these quantum computers that are based either on ions or atoms. So the states of these elementary particles, which are used for the computations inside the quantum processor. And it's something totally different than the Intel chip that you find inside of your PC. So you have these particles which are kept in a vacuum chamber, held by electric or magnetic fields, addressed by lasers, and only around that you have the standard electronics. Actually, this is what Creotech is working on, the electronics that is controlling this quantum heart of the computer. And then you can also introduce cooling. So for trapped ions or atoms, you don't necessarily need to cool them down for the quantum computer to work, but for superconducting qubits, you need to introduce really low temperatures, colder than in outer space. And that's why you have this gigantic machines that you see in IBM that look from a science fiction movie, but they're actually really big coolers to keep the quantum heart of the computer cold. So we're actually building these machines, and they're at this moment taking quite a lot of space. They look robust, but they actually work and now allowed to develop first applications. And this is the really super exciting moment because we're moving from this engineering challenges to actually software and algorithms challenges to find out how to best use these quantum computers and obviously also develop them further. So yeah, that's what's happening now.
Yeah, I think that the mystical part comes from the type of problems the quantum computers can solve. If you look from the point of view, or rather with a Turing machine or a classical computer in your mind, they can do magical things. Like, for example, you have an energy landscape and a quantum computer can just say, well, yeah, here is the optimal point. Yes. But if you think about it, you can do the same thing. I mean, if you look at a mountain range, you can just naturally say, well, that is the highest mountain. A Turing machine can't do that. It will have to do some computing intensive hill descent or ascent algorithm, and that will take time. And that's why they look magical, but in the end, they're very natural.
I mean, this is the most natural thing to do in the quantum world, to find the lowest energy state. So yes. Exactly, a totally different way of approaching problems.
Yeah. Okay. So it's. I mean, definitely, optimization problems are like one of the biggest, let's say, potential use cases for quantum computers. Just you know, still it's like not okay. I'm by the way, I should disclose I'm a bit of a on the skeptical side here. Just always
forgot to mention that he's our pessimist. He's our optimist. He's our pessimist.
Definitely. Although I'm super excited about quantum computers, of course. So right, one should always like remember to compare with the performance of the best classical algorithms, because often what happens is that, you know, for classical optimization problems, there exists fairly good like classical routines already out there. And okay, this is mainly because people were interested in those problems, and for many years they were developing it. Just quantum computing is relatively new, so perhaps we'll figure out how to do it better. But I should maybe add that okay, for quantum optimization problems, quantum computers, this is like the area where there is, I would say, the biggest hope and we have the biggest confidence, like when it comes to kind of understanding structures of like proteins or some chemical compounds, for example, because the optimization problems there are kind of itself quantum, itself magical, so it's not so straightforward. Yeah. So.
But I don't know if you agree with me. From my point of view, as a person not directly involved in the development of those algorithms, but following the field, I think that the super exciting idea is to first also develop classical quantum hybrid algorithms.
Definitely.
That combine both classical and quantum resources. And then we can use the power of classical computers that is really well developed and understood now, but at the same time take advantage of the things that quantum computers already start to do better than classical computers. I mean,
exactly. I definitely agree. This is like one of the main trends that is out there now. I mean, one of the reasons is what you said. The other is computers that we have at the moment. Like they are not yet fully scalable. We hope they will be soon.
We're working on that. Yes.
Yes, and then it's like doing this hybrid classical quantum approach is then the way to go. So for you combine power of classical supercomputers with some limited, but very interesting still quantum part, and then you can get some nice advances. Yes.
But all that pessimism, it reminds me of the beginning of the 20th century, when we had the first cars and people were saying, you know, my horse is stronger, my horse is faster. It will never be a thing. And see where we are today.
Yeah. Sure. Just, okay, maybe my personal, no, I'm just personally super interested in trying to sort of understand, you know, the difference and the like boundary where the power of quantum lies, where the power, with respect to classical computers. So, okay, just I share one kind of counterintuitive story. Sometimes, actually, quantum can help classical devices, okay, or classical algorithms. So people were thinking in the context of machine learning of some big speed-ups, big advances that you can get, say, in recommendation systems using quantum algorithms. But then clever people came and they realized that actually you can get you can look how the quantum algorithm works and write the corresponding very nice, very efficient classical algorithm, which wasn't there. So, I mean, for many problems, we don't expect this to be the case, but also interaction, like this interaction and interest in the field can bring something even, I mean, some advances not only from the quantum realm to the game.
But
yeah.
Moving back to the quantum machines itself, it's not that we will get rid of classical computers at all in the future. They will have to cooperate each other. We still need classical computers to control the quantum computer. And it's not that in the future we will have quantum computers that you can put on the desk in your office, or you will have a quantum processor in a mobile phone. It's more that there will be some quantum computation centers available via cloud or internet that can support you in doing the very magical calculations that are not possible currently.
But again, maybe.
Right.
I mean, a computer is not just a faster horse. It is like a car. It's an entirely different thing, and it might lead to entirely different things. And we are limited by our own imagination. And if the silicon-based quantum computer would work, that might be something that is reasonably small, that in 50, 100 years can just fit in my pocket and supports the AI that I have there.
But like talking about the differences between the quantum computers and the classical computers, we can like say that like the development of science through all 20th and 21st century, it just pushes us into the arms of quantum mechanics. And to mention that the quantum mechanics arose so controversial at the beginning of the 20th century that Einstein himself couldn't accept it. So, but today, the quantum computers that until recently were just the domain of the theoretical physicists, they became real. Yes, and we replaced just the classical Maxwell's equations by the laws of quantum physics, and it makes the quantum computers, they are not just the faster counterparties of the classical computers. They are something which is fundamentally different. And it's not only engineering that need to improve to make it available. It's also about the computer science itself. So, Michał, can you tell us, like, we probably will need completely new programming languages, the new algorithms, the new computer science will emerge in the near future. Am I right?
Yes, so like the end game is to actually present, like to hide all this quantumness actually. So you want to sort of, have those algorithms kind of presented in a black box so that the common people can use it. They don't have to dive into peculiarities of quantum mechanics. Although now, still we need to understand physics and like limitations and specific features of those devices to make the best use of them. Okay, so so computer science, as you might ask, then needs to incorporate those features. So you need to know what are the how difficult it is to run certain gates on your algorithm, on your computer. What is its connectivity? How many gates you can tolerate before the coherence or noise kicks in. So because of that, actually competences at the interface of physics, computer science, mathematics are needed. Because imagine you are you want to make some practical use of your device, right? You're working at some company, and you don't want to spend crazy lots of money for for repeating some not very useful thing, because this is the way that the things work now. So you for every experiment you actually pay to vendors, right? So you want to organize your algorithm in such a way that the overall cost like in time, measured in time or money, is as small as possible, right? So, therefore, some competences at the interface of those disciplines are really necessary.
But I think it's also worth mentioning that on top of that, you also need people who understand where the quantum computers are actually most useful, because this is a different kind of computing, and it will actually show its advantages in very specific applications and very specific types of codes. So also building this quantum readiness or knowledge of quantum technologies on upper levels of management, that you know where to invest and what kind of algorithms are interesting for you, what kind of features of quantum technologies or capabilities will be relevant for your company. This is yet another set of competences which is needed right now from the other end.
Like, so can we say just like the future computer science, we can just divide into 3 areas. The first is the very technical one. For example, the theoretical error correction that will make actually the quantum computation to happen. And the second one is like the development of algorithms, something that I know in the business language we can say that it happens in the back office and the customers, they don't see it. Take, for example, the famous Shor algorithm, which actually is based on some quantum mechanical features of states, and you cannot just invent it in the realm of classical IT or classical information theory. So we need people who will work in the back end just to invent these new algorithms that will solve new problems. But then we will need people who will connect it to the wider audience, because we don't expect any business users to learn quantum mechanics. We just want to give him the tool, some user interface, some very common programming language that can leverage on the quantum computational power. Isn't that like that?
I think that is part of being quantum ready at this point. So now the quantum world is comparable to the classical computer in the 1940s. The concept works, the machines are bulky, it's kind of hard to work with it. And there is a whole transformation that we have to go through. And it's best to be part of it, to help it shape and see what we can do with it. Because we have indeed some algorithms. You mentioned Shor algorithm. There are a few around, and we know that quantum computers can answer a few questions, but maybe they can do so much more. But first we have to have the machines at a different scale. We have to have more interest, so there is more capital in the industry, and then it will all come into some exponential growth phase that will probably change a lot.
So the best way to gain the interest by showing the audience what can we achieve with the help of quantum computers. Like as we said, we have like new machines, completely different than the classical ones, based on the completely different physics inside. We have like new algorithms running on them, and then we can try to tackle the problems where we can try to solve the current problems in a better way, or even we can try to tackle problems which are currently completely unsolvable. It's like that. This is the power of quantum computers. Philippe, do you think?
I kind of think it is better to be careful and to manage expectations and not to overly say there is a certain hype around quantum computer, partly because it is mystical and those machines can do things that are magic for us. They do absolutely fantastic things. Quantum mechanics is magical, honestly. I never understood it during my physics classes. I never truly understood what quantum mechanics is all about. But the problem is that if right now you publish, like 100 years ago in the New York Times, that we will in 1 million years not be able to fly, well, you can be wrong, and 9 days later we can fly. But you can be right also. Probably the truth is going to be somewhere in between. Quantum computer is now largely in an engineering problem phase, but once that engineering problem phase is solved, then we need indeed to solve, then we are able to approach the problems of what other questions can we answer with quantum computers. One of the things that I'm personally most excited about is solving cancer. Understanding protein folding or other problems that look complex to us, but quite probable, but they are based on quantum effects. So most probably those things will be natural to solve for quantum computers.
So maybe it would actually also be useful to say what are right now the top use cases for quantum computers. So obviously drug discovery, problems in biology, then problems in chemistry. So in particular, people are hopeful that quantum computers can help with the development of better batteries with better parameters and properties, but also, for example, solving problems with manufacturing of nitrogen-based fertilizers, which are connected to a very large industry, actually. Then logistics, transportation, quantum-assisted machine learning is also a very promising avenue, and also obviously finances, so portfolio optimization and predicting how the value of your portfolio is going to grow or behave in the future. So these are the use cases which are being actually tackled right now, and there are some specific simple experiments with simple algorithms on quantum computers already performed and studied, and actually already first advantages over classical computations are being shown right now. So this is already starting to move away from the field of science fiction and becoming reality. How much impact it's going to have in the nearest future, we don't know yet, but it's definitely very interesting, and it's definitely worth to already be aware of what's going on and try to be part of it.
Can I throw in a bit of skepticism?
Of course, please do.
Yes, yeah, a skeptic of this crowd. So, right, so right, it's super exciting, and I agree that there are big chances and opportunities that lie in quantum computing, in quantum algorithms. Just to be kind of clear, at least according to my knowledge, as of now, there were kind of no actual advantages demonstrated for any, let's say, for any practical problem using quantum as quantum computer. Just I want to say now on the positive side that there are there are experimental demonstration of some particular tasks by, for example, Google that are not practical, but let's say provably you outperform classical computers. That was this famous experiment of quantum advantage from 3 years ago now, right? So there are some, both experimental and theoretical, let's say, underpinnings to this let's say optimism, right? Also I would maybe add that while let's say especially for chemistry and quantum, for solving ground state problems, let's say we know there exist algorithms that would fly on those scalable fault-tolerant quantum computers, but currently we don't have them yet, so we need to explore the options that we have, right? So that's obviously currently, but still there is lots of reasons for optimism. Yeah.
Obviously we're just at the beginning of the road, but it might be that actually in the end quantum computers will find their main use and advantages in types of problems that we don't imagine yet, the kind of applications that will win in the future. We don't know, but it is definitely interesting to explore this new tool because it's based on using yet another new technology coming from physics. And we've observed in the history of humankind and the evolution of technology that many breakthroughs were related with harnessing new realms of physics like electromagnetic radiation, radio, electricity, nuclear energy.
Yes, and even thermodynamics with a steam engine.
Exactly. So we don't know how the future will look like, but exploring the potential of these technologies now is highly relevant.
It is.
So maybe let me say that our goal is not to blow the quantum computers bubble and to make it to hype, but I have this feeling that it's not bad to dream, because even when the dreams, they are not reachable, they are showing us the direction. And I think that when you look at the market, you see that some of the businesses, they are already heading into that direction. Like, for example, very recently, EY made a survey among executives in the UK, and almost 50% of executives believe that quantum computing will interrupt their businesses by 2025. Wow. And among the industries, the most interested in quantum computing are the industries like pharmaceutical industry or automotive in designing the new batteries. Because, like Feynman said, you cannot model the world with help of the classical computer because world is quantum. And to discover new drugs and discover new batteries, you need to make those simulations. So you should use quantum computers to do that. But the quantum computers are also very effective in solving the optimization problem. And that brings banking and finance into the field because they are investing a lot of money, like your bank and other big banks, they're trying to investigate the way how quantum computers can help them in, like, risk management, portfolio optimization. And it's even written in the net zero agenda because you can try to replace this energy consuming HSBC centers by quantum computers. Like, can you say something about it, Phil?
Yes, that is indeed one of the things that makes me enthusiastic about quantum computers, even if they wouldn't have necessarily an advantage. But if you have the choice of running a computing intensive thing on a classical machine or on a quantum computer, you probably go for the quantum computer out of an ecological consideration because it will use way less energy. But about the banking sector is of course very crucial and important, and the quantum computers have certain things that you have to be very careful with. For example, the quantum computers at some point could be able to break encodings or encryptions that we're using today. Like the simple public key, private key encryption that we use is very powerful and almost unbreakable for Turing machines. And that's why we use it. So whenever you have HTTPS on your screen, so whenever you're buying something on Allegro or doing a transaction with your bank, you are using that type of encryption. Well, quantum computers, maybe at some point, they can break that encryption. They can just guess your password, so to speak. That is a big threat. So for banks, it's crucial to be on top of it to understand what, when, how. Of course, there are ways to encrypt that with the quantum computers, or at least the knowledge about quantum computers that we have now, we might not be able to encrypt, or you can even use quantum mechanics to your advantage to encrypt it in such a way that you are absolutely sure nobody has ever opened your message. Optimizations obviously also are a big thing in banking. Think about financial markets, and financial markets typically are accessed through banks, so banks are a very important player and a very important custodian of the safety of those international financial markets. So also there, it is very important that the banks understand what will be available when, and already now start working on such things so that quantum computers first get into the hands of responsible organizations instead of in the hands of the hackers to guess a password or to abuse trades on financial markets. For example, if you have a big transaction to do, you cannot just put it on the market and let people buy whatever you have to sell till it is all gone. That will be detrimental for the price, and you will have a very bad price. You will push the price down. So you will do different ways of putting that on the market, so not showing what you're doing, in order to avoid that high-frequency traders eat up your profit. And for example, you are doing that for a pension fund, legitimate reason why you are selling those assets. So if the other party has a quantum computer and that quantum computer is able to figure out things better, well, then you are at a disadvantage. So as a bank, I think you do not really have a choice. A bank, more than any other type of institution, is a custodian and is like the heart of the industry. A bank is a facilitator and has a very responsible role to play. So banks have the responsibility now to understand what is going on in the quantum world and to see what we can do. And so those are the two big parts, the encryption and the safe holding of digital transactions and interactions, optimizations, and Obviously, there is a whole third part, like, for example, if we have quantum-enabled AI that works better, well, then we can have a digital assistant, but okay, that digital assistant can sit in your car or can replace the bank teller, for example. So in that part, bank industry probably isn't outstanding.
Quantum computers might also speed up Monte Carlo computation. So that's another point which might be useful for a finance.
And there is something very interesting, sort of very simple, like to do Monte Carlo simulations, you need random numbers.
Yes.
Well, true randomness comes natural for quantum computer, and it's pretty hard to find for Turing machines. So even just finding random numbers is such a great application.
And a simple one, which is achievable in the nearest future, obviously.
Absolutely.
Yeah, it's actually people already did this kind of experiments, right, in the context of like Bell tests, right, like they generate. Yeah, okay, but actually people actually already use generation of like quantum generation of random bits, like for crypto, for example, right?
Yes. So here is a first application that already works, isn't it?
Sure, sure.
So far, we were discussing the possibilities. We described the future that we all hope that it's not a far future. We dream about it and hope that it will come sooner than we expect. But there's still an open question about today, about how we should start preparing ourselves for quantum era. Is it that we should start investing in quantum technologies today? And it's not only about the financial investments, which actually grow exponentially. Since 2019, it grew to around $1.4 billion in 2021, investment in quantum computing. But it's also about how we should prepare our organization for quantum era. And I would like to ask Anya, because Anya, you are actively working in this European Quantum Industry Consortium. You are the co-leader of one of the working groups called, I need to look at the Market and Technology Intelligence Working Group. So this is like the organization that is trying to connect the market and try to prepare the market as a whole for the quantum era. Could you tell us something about that work?
Yes, so that's actually a very interesting initiative that happened in the recent year and a bit in Europe. So the European industry started to collaborate more intensively, and we formed this Quantum Industry Consortium that gathers both companies working on quantum technologies themselves, so for example building the quantum computer hardware or software, but also other stakeholders, so potential users, venture capital funds, consulting companies. So we're trying to build this European quantum ecosystem in a sense and support the development of these technologies, be also the power for lobbying, for shaping policy in the European Union for quantum technologies. So we work on various topics. So we have a group focused on education. So first of all, defining the skill set that we need to make various industries and sectors in society quantum ready. But we also have work groups focusing on the state of the art in quantum technologies, focused on the strategic industry roadmap, so how the technologies should evolve in the future. And also work groups actually trying to define the most promising use cases and figure out on how to implement them in the best possible way. And this is already supported by really strong industrial players from various fields. So we have various strong players from industry supporting this initiative. We have companies from the pharmaceutical sector, from chemistry, from more hardware-oriented industry like Bosch, but there is Roche, there is Merck, there is BASF, there are consulting industries. This is a really interesting group of stakeholders, of companies, and an interesting place to network. You can see how quantum technologies become interesting to various sectors already right now. Also, I think what it might be interesting to people from Poland who might be listening to us today is that in Poland, in Poznań, the Supercomputing and Networking Center has already a good collaboration with IBM and is trying to create a hub for developing quantum algorithms, and they have also applied for funds to host a quantum computer on site in Poznań. So if this works, we might have in Poland also a strong center for development of quantum technologies for the future.
Let me just also ask you, Philippe, because you work for the organization which seems to really understand the meaning of being quantum ready. Like when you look at the press release, HSBC appears very often as one of the leaders of becoming quantum ready. And your personal perspective, how do you think the organization should prepare themselves to quantum era? What are the steps that they need to take?
It's a very interesting question with a few parts in the answer, I think. First of all, banks in particular, they are on financial markets. And when you think about it, you typically think, well, it would be great to have the quantum computer first. Because if you are first, you probably have some advantage and you can exploit it, probably for a short while, and then everybody has a quantum computer. And in the end, just like Turing machines, they transformed the way we do banking, but they didn't transform banking itself. And so you will just have to adapt to it. And you can be a little bit late in the process. Nothing dramatically will happen, I assume. But banks also have a certain responsibility. Banks are those that have to keep people's assets safe. They have to keep transactions safe. They have to keep the financial markets safe against abuse. And so there are some dangers or potential dangers with quantum computers, like, for example, they could find out your password or something related to that, which basically means that the bank put in place a transactional system where people can do can wire money, for example, and at some point that can be compromised. Well, you have been warned. I mean, as a bank, you do not really have the option to say, I didn't know, and now suddenly there is a hacker with a quantum computer and my system doesn't work anymore. If you have seen this movie, then you know that that is around the corner, which basically means that as a bank, you, instead of an opportunity, you have a responsibility to find out, to know, and to be prepared. And I think that is the first and foremost things that financial institutions should try to achieve with their quantum approach. Keep customers, financial markets, and transactions safe. And so the way to do that, fortunately, it is not too difficult, because there are these industry platforms in which you don't have to buy a quantum computer and hire a small army of specialists to run the machine. You can network, you can find out things, listen to movies like this, come to those platforms, find out. That is the first thing to do. And then the second thing to do is to be part of that evolution and contribute something back to society by investing in it, by making sure that we have software that can solve problems that are practical. And so in the end, it's an ecosystem where everybody will be better off if there is more interest in quantum computers.
That's a good answer. Thank you for that.
Thank you.
So, like, we are running out of our time. So let me just summarize that. Like, recently, quantum computers have grabbed widespread attention, which is driving a shift in how it is perceived, taking it from the niche technical curiosity to the serious topic occurring regularly within the mainstream business technology discussions. And quantum computers may just be emerging from the science labs, but its transformative potential suggests that the business have no time to lose in preparing for it. I would like to thank again my guests. And at the end, if you want to add something from yourself, just feel free. Maybe from this side, Philippe.
Okay, thank you very much. So it's really a great time to be alive. Just turn back the clock 100 years. So many things were different. We had no ideas that other galaxies really existed. Cars were not really functional. We had no computers. The world is totally different. And it is changing as we speak, and we are part of it. That's a fantastic thought. Thank you.
Thank you. Anya?
Well, from my side, I'm really looking forward to how these technologies will develop and where they are going to surprise us. Because I'm sure that in the end, we're going to do things that we don't imagine now that are possible with this kind of technologies or similar ones implementing quantum physics. And by the way, I'm sure we're also going to develop exciting new skills in other fields, like in the hardware industry and in the way we build classical computers as well, in integrated circuits. So these are definitely exciting times, and hopefully we will use them really well.
Thank you, Anya. And Michał?
I'm also excited, and I'm looking forward for the future, because quantum computing goes away from being just a field of academic study and can soon become something practical. And I mean, for me as a researcher, it gives some chances, and me and my colleagues to work on new exciting projects and problems that can be maybe useful for some, for practical things. Yeah. So.
Thank you, Michał. Personally, I can't wait to see all the benefits of the quantum computers coming into the real life. But in the meantime, please become quantum ready and stay tuned with us, because there is much more to come with our EY Academy. Thank you.